You can see slides, right?
Yes.
Okay, so today's October 8th, and we will talk about Mixer, but we also will talk about scaling laws, and we also will talk about some MLP-like architectures which are also published after MLP Mixer. So basically, Mixer is another type of network which kind of battles convolutional networks and visual transformers. And I think there is a question what actually we need. Do we need convolution, or just we need self-attention, or we need just MLPs? But recent works saying that you just need patches. It's not about self-attention or convolution or MLPs. So let's go over architectures and just think about what we're doing in the architectures. So we're doing like mixing of features, and we can mix features at given spatial location or between different spatial locations. And simple examples, n-by-n convolutions, pooling, and we basically mixing features between different spatial locations. And we have one-by-one convolution, which is point-wise convolution that performs mixing of features given spatial location across channels. Large kernels can perform both 1 and 2, and self-attention allows to do 1 and 2. For example, you're using MLP in self-attention, you mixing features at given spatial location, and then you through self-attention you perform mixing through different spatial locations. And regular MLP just do mixing of the features at given spatial location. So this kind of summarizes all basic building blocks we're using in architectures. And I think the main interesting work has been vision transformer. Basically, what we're doing here, we just creating a sequence of patches from image. They did just like non-overlapping sampling of the patches, and then they feed these patches to the linear projection layers or convolution layers, and you get some embeddings, and you perform encoding using transformer architecture, which is on the right. And basically, starting from embeddings level till the end, you have isotropic architecture. It means that each layer basically takes the same size as the input, and there are a couple of like tricks to make it work. For example, you have to add position embedding, but it's not important every time, so it's still kind of choice. And in Vision Transformer, you also add additional embedding, which they call class token, and it's learnable embedding that basically uses just for classification in the end. But it's just like choice how you can do it. For example, you can don't add this class embedding and just use global average of your embeddings to perform classification. So there are like many choices, but like main idea is that you're creating patches of your image, and then you're learning some embedding of these patches and passing it through isotropic architecture is stacked from multiple layers. So this is like main idea, and this idea kind of extended to Mixer, which is shown here. So you can see the structure is basically the same, but you don't have this class token, which is extra learnable token. By token, I also mean embeddings. It's just like different words, different naming. But like the main idea instead of like using this right transformer like self-attention building block, we just create a building block through two MLP layers, and one of them just perform mixing over channels. And so if you have patches like this, so basically mixing over rows, and second MLP mixing over columns. And it's like two-step operation. Basically there is nothing like much from this architecture. You're just separating mixing of channels and mixing of tokens. Like first you're working over rows and then you're working over columns. The main difference will be in complexity because the self-attention, it will be quadratic. Here it's like linear because you're operating per location. And another, I think, important step here is that parameters of the channel mixing are the same for each kind of location. So it provides like the same ideas in convolutions to provide this positional invariance. So it doesn't matter in which row you apply channel mixing, you're applying the same weights. And they found to be it not important for performance, but it saves a lot of memory to perform this channel mixing operation. But there are like some cases when you couple, there are cases where you can apply different weights for different location. So it can be called as a separable operation. So there are separable convolutions that apply convolution to each channel independently. But by tying the parameters, like making them shared across the channels, you're saving a lot of memory, and I think it should be statistically more efficient. And
so,
what,
Alex, can you just discuss the details? So there is only one MLP for channel mixing, and there is only one MLP for what do you call it? A cross pixel mix. What is it?
Spatial mixing.
Yeah.
Spatial mixing. Okay, so it's parameter tied.
Yeah.
And then you have multiple layers.
All
So this
what's
this
different than convolution than convolution?
Well, so because they do weight sharing over the channels. That's it.
So
No,
they're
it's not.
applying to the image and transpose of the image.
I mean, it's very simple. Yeah.
So I mean, you can see formulas like here on top, and they basically it's like applying MLP to the data, and I don't think it's like different. You're just using a lot of like skip connections, and you're adding some like layer normalization, but overall you have just two-layer MLP like this building block.
So is it like for the transpose for the channel for the first one? The first one is basically different.
Yeah, that's what they say in the paper.
Yeah, I mean, so like so building blocks.
It's like one convolution with kernel one, but it's like very strictly.
Yes.
Only make the output not one but wider.
So it's related to this like depth-wise convolution when you apply just convolution across the channels, and then there is point-wise convolution kind of. But like you can think it's better like in rows and columns. First you apply across rows and then you apply across columns. So if you have data like patches by number of channels.
So did they try, why is there a significance in applying to channels first and then to the spatial mixing, or it doesn't matter?
I think they just pick the order.
I think they do channel first and then special
Yeah.
mix.
Well, I mean, that's what the figure says, but I mean, does it
Yeah,
matter?
whether it matters, I don't know.
I think I don't remember there was like this, like the difference, but
With the skip connections, it shouldn't have to matter, right? Because you can just learn.
It's quick, skip
I-
connections.
I think
Yeah.
might be like they check the performance and choose this way. So it basically like we can think what channel and token mixing does. So you want first to mix the embedding itself, and then you're mixing. So like first you performing operation on your token, and then you measuring across the tokens. So you first encoded the token, and then you kind of connected your tokens with other tokens. So I think basically you preparing the token to some kind of space, projected space, where they can interact with each other, for example. But of course, I think you can connect them first and then propose this. But I think self-attention relates your activation with respect to similarity, with respect to dot product. So it mixes first, and then it connects to them.
I think they're part of the reason why they do it is if you think of it as like with channels in terms of like features, if you first learn sort of a new projection of your features and then learn the spatial mixing, you can like put your features in a new space, and then you can learn sort of the similarity. Because the second one, the spatial mixing, I mean, it's done with an MLP, but you could replace that with a self-attention layer. And then at each of these blocks, you'll get the self-attention of each sort of token with each other.
So it's kind of, I would say it's like first step of this. So I think this part, like specifically until this class before the MLP, like they kind of swapping this multi-head attention with this approach, which is linear with respect to number of pixels or number of patches. Should we go forward, or
Yes,
the
yes,
rest of the question?
go
Okay, so there are like much more work, and I just put it here just to show people that there are different ways how you can do it. But it just basically, to me, it's like architecture search, which is better. But if you're interested, you can actually look these papers. So I didn't like read all of them, but I just put them that they exist, and there are just like small changes. I think they added like some additional layers here.
Yeah, so here they do it the opposite way, right? They do cross patch first, and then they do cross channel.
And the skip connection would not compensate for that, because in the previous year, right, it was coming to the channels, and here they bypass this whole thing. So here the order matters.
Yeah. So I think it's like the extended, I guess, this is like MLP mixer layer, and then yeah, it's this additional layer. But I might be wrong, but
It may,
Okay,
is
this
it
is
made
what we
difference if
do.
they do like an affine thing, because the cross patch sublayer, isn't that similar to what they do in the MLP mixer? Isn't that the second part of the MLP mixer?
I think it's the same. Like, yeah, maybe like it's just basically the same building blocks. You want
Yeah.
to mix the tokens, and you want to mix it within the token. But like I think like the definition I kind of mix it around. They're using own words, and like I think if we use like patches channels and just define dimension, then it will be easier to understand, I think. But the main idea is just like you creating a simple MLP layer and you just applying across rows and then you're applying across columns. And I think this is like main idea. But you can add a lot of stuff here if you want. But it's just basically architecture change, I think. So there is like paper gated MLPs, and then they add like special gating unit, so they changing the token mixing path, as I understood. So this is like again extension of the MLP mixer. It just performs better, and I wonder like if we can use just like LSTMs here. It's also gated but smarter. But
LSTMs are not fit for the training in the modern architecture. This will train much better, faster. It doesn't have to wait. There is no recurrence.
Yeah, there is no recurrence. But it's just basically, I guess, additional gate to select features.
For temporal data, this would be really cool though, because then you could do something where you do use MLPs, because if you have like the spatial gating unit, you could also do like a temporal gating unit, and then you basically kind of get your LSTM back.
But I think it will be hard to.
Recurrence.
No, but so for temporal data, I'm saying.
But I think it will be hard to backpropagate this thing, because transformers and MLP mixers are working a bit different than like LSTMs, like because you in transformers you're considering a time point using the same encoder, so you don't want like to make them unrolling, because unrolling will reduce your this like parallel data efficiency, and I think that will be the main problem.
But I think LSTMs are a little more efficient though, right, in terms of parameters, aren't they?
No, it's not that this is the problem. The problem is
No,
that for every time you have to wait for the previous time.
No, I know.
You
Yeah,
can't,
so
and here you just commute everything in parallel.
Oh,
Yeah.
But you need more parameters because you need to take all the inputs at once, like the whole sort of time series that you want to do at once.
Yeah.
The window.
People are happy with that.
No, I know. With our computers right now, that's the.
Waiting is more costly than space.
Okay, so there is gated MLPs. It improves on natural language processing and computer vision. Then there is like new paper, which is 4-page ICLR 2022 submission. And basically they put in convolutions again, and they beat all the gated MLPs and MLP mixers. And you can write this implementation in like 7 lines if you want, or like 280 characters. There have been like hype in the Twitter recently, within like last 2 days. But this architecture, I think, state of the art right now. Yeah, so, and the main idea of this paper is basically says we don't need convolution, we don't need attention, we don't need MLPs. Basically, what is making these models work, it just patches in the way how you process them. So to me, it's like, if you think like how convolution works, convolution basically works on like some patches. Like you just give one patch and you getting representation. In this transformer and mixer architectures, your patches kind of interact with each other through additional layers. So, and I think it's kind of, you can think of it like back of words. Each patch is just a word and you have a back, and you're basically learning interaction between these words in the back. So I don't think like we advanced in ideas so far, like very far away from this kind of notion. We just creating better architectures for the same problem.
I don't see, Alex, I don't see how it's a bag of words, because you are learning or exploiting spatial correlations. You're not ignoring them. They're not really parallel, they're mixing. So
because bag of words is very like abstract. I'm not saying like to details. I'm just saying the word is a patch, and or token. It's like bag of tokens, and you created a bag of tokens just for specific one image, big image.
but it's not a bag. It's you are considering interactions between them. You are considering it's kind of the same idea that its convolution is exploiting spatial correlations. You're still exploiting this spatial correlations. Stride equals the size of window.
Yeah, but it's more locally. Like even if we use convolution, it's like local on a patch. Like convolution is just operation. I want to abstract away that like given an image, when they subsample it on this non-overlapping grid, they're creating some like local description of this image. So for each image, we're getting back of words or tokens, and then we have layers which work on a token, and then there are layers which kind of connecting these layers, like the connecting these tokens.
Connecting, yeah, that's the point. If you were intermixing randomly those patches during the training, then it would be a bag of words. The order doesn't matter. But you cannot do that with these architectures because they are exploiting spatial relations.
That's not completely true because for convolution, yes, they do, but they work completely different than transformers. But for transformers and mixers, they're more robust to permutation of your patches and permutation of the pixels inside the patch. But global shuffling of pixels will make them like less robust, like they will be allowing performance. We will see it later, but CNN will completely fail. So I understand your points, but some of the like parts of mixers, they're more like robust to permutation. So even like there is a paper which uses permuted input for the agent, and it shows that agent can still perform even the patches shuffled within the image.
Even though it was trained on different permutation.
Yeah. And we'll see also here. So it's all connected. So the main idea, like if we just watch on, if we compare like regular convolution network with transformer kind of architectures or mixer-like architectures, the main difference that CNNs are pyramidal. So we basically are increasing by each layer receptive field, and we lowering resolution. In mixer or transformer, the architecture is isotropic. So we have a tokens that can have receptive field, like maximum receptive field available because they interact between tokens. So, so this doesn't apply to CNNs. In CNNs, we have fixed receptive field, and we also allowing resolution every time. But people saying that this kind of creates inductive biases of our architecture, and that's why CNN is still efficient. And that's why people trying to create inductive biases of this kind of pyramidal structure in the images with transformers. There are like a couple of works I know, but they're not here. But I think it's like big kind of picture. Maybe I can be able to do this kind of overview and connect all these pieces. But just I think that backward idea is kind of very like similar to this. like if we abstract away this like architectures itself and think of them like just simple transformations. Okay. So this is conf mixer, and there are different modification of mixer MLP. I didn't read them, but I don't think like they went far away. For example, with this one, when you're mixing tokens, like within location, they mix it here a bit different. They just going, so if the image like width by height, the tokens in vMixer MLP considered as like just sequence. Here they kind of performing projection with respect to width and height separately. So it reminds me pyramidal LSTMs from Schmidt-Huber group. Basically reading your image with different directions. And I don't think like they improved that much, but it's another way how you can mix your stuff. And I think that here they changed how you mix the tokens. So you mix first spatially and then you mix channel-wise. So it's so I think it's related to the question you asked, Dr. Please. So I think it's just choice, and you have to see whether it's better or not. And there is cycle MLP, so it's also modifies how you want to mix your sequences. So previous one, vision permutator, did with respect to width and height, and here you just do cycle-wise. So you have less complexity, and you basically don't check all the tokens, I think. But it's all like small tricks, and just people basically running architecture search of what should work out better. And I'll just talk about how to train a MLP mixer. So in this specifically a paper, this group working with big data sets like JFT 300 millions, and they use also ImageNet 21K. It's 21K classes in regular ImageNet, and for most of the models like MLP mixer or vision transformer, they used to pre-train these models on a big data set, and then they transferred these features to small data set to create state-of-the-art results. And basically this approach to solving the problem, I think related to the scaling laws. I will cover this like a bit later. And I think notable from this training pipeline for MLP mixer, I think we should consider maybe weight decay, gradient flipping. It helps regularize the model. As after claims like MLP mixer is easier overfit compared to CNNs or vision transformer. They're again using like standard techniques like random augmentation, mix up. They also add dropout and stochastic depths. So stochastic depths is basically controls how many layers of transformer or mixer you're using during computation. And a lot of stuff to do that you can find in team library. Sorry, this Apple check. Apple changes the word, but it's called team library. You can see here.
So I have a quick question. I wanted to ask, so about random horizontal flipping in this particular context, right? All it's essentially doing is reordering the order of the patches, right? Right, that you're sending into the model. It doesn't really, with this patch representation, you're not like convolving differently at all.
Yeah, I understand, but I just, I guess we have to understand GFT 300 millions because they do it specifically for this data set. So there is like specific paper explaining this step. So I didn't read it. And
yeah, I was more just like asking, like, so for these kinds of data augmentation and patch representations, like, you know, isn't there a way, or I don't know, some way we could exploit the way that this patch representation is in some ways just like represented as a permutation of patches for so many like standard image transformation types, like flipping, for example. You know, just like a random thought. I don't know.
Yeah, so to add to that, I know there is a algorithm called random patch augment, which basically each patch has its own augmentation. So it might answer this question, but somehow I don't see it here. There is this like random patch augment paper also. I think in the most complicated scenario, it uses reinforcement learning agent to control how you augment your samples based upon the performance of your model. So yeah, there are multiple ways how to make it more complicated and maybe improve. But I think like the main idea of this MLP mixer paper is just to show that you can still construct the models that are based on MLPs, and they're not like that bad compared to CNNs on performance. But they also want like to create the models that are much more scalable to the big data set, because it's Google and there are like Facebook works on this, Microsoft and other companies. And I think the main idea is just to understand how, what kind of scaling laws in these models, how we can, like, we should understand better how to train models. Do we need like really this huge compute and huge scale, huge data sets, or till what kind of degree we can learn our models? And I think there are like a lot of tricks you can use. But like, even like we're using tricks, there are still ideas that there is scaling law, which kind of predict your performance. And you might not go above this, even like you searching all the kind of models you want. And there is like other problems called under specification, because we can have models which perform like quite similar, but they're using different solution. And this different solution can be, in some like very extreme cases, very orthogonal to each other. And I have links like in the end of this presentation to explore this question. So they use regular GD patch size again. There's typo. It's 512. So they use small batch size on fine tuning. They still perform gradient clipping. They use cosine learning rate schedule, and they use linear warm up. So you basically warming up your weights first. As I remember, it was like 10,000 iterations. And then they also fine tune at high resolution. And the fine tuning on high resolution is also engineering question. So when we increase resolution, we have just like bigger number of tokens. So our sequence get much more longer. And in MLP mixer specifically, to deal with different resolutions, you have to take first layer and created with new segment lengths. And specifically in this paper, they're taking previously trained weights on, for example, resolution 224, and then they create multiple copies of original pre-trained weights to a new network by copying over diagonal. So you're basically stacking block diagonal matrices, and you can do it only for the size of images, which is like double of your original one. So for example, if you have 224, you can do it to 448. So this is another engineering point you have to consider for this kind of models. And we'll talk about experiments and discuss some questions about scaling. So the main results showing that mixer performs well with respect to vision transformer or big transfer. Big transfer is a huge ResNet, which was pre-trained same way as this mixer on huge dataset. For example, you train on ImageNet 21K, and this performance on transfer learning for ImageNet. Real means that there is deduplicated ImageNet. So it's basically ImageNet with cleaned labels, and there is average 5 means there are 5 different tasks. And this performance on 5 different tasks. And there is that set, which is VTAP. It has 19 different tasks for transfer learning. And this is like average performance. And there is also through output, basically how many images in second you can process with this architecture. And this is computation in TPUs that Google is using. You can see that mixer is kind of very close to the vision transformer and big transfer, and it outperforms big transfer a bit on bigger scale, but they're very comparable to each other. I think this table doesn't show everything, but if we're going to this picture, you can see if you're increasing training size, mixer performs quite well and better than vision transformer. And one can say that MLP has like less inductive biases constructed in the structure compared to self-attention, for example. And self-attention leads to some certain properties of the function. And that's why mixer kind of interesting in the sense that with larger training size scale, you can get better performance.
I have a comment about. Can you quickly flash the table on the previous slide?
Okay.
Yeah, go back to the figure, please. So I have a comment about the figure. When they're computing those dots, those lines on the right graph, is it linear 5-shot ImageNet top 1% over a holdout, right?
So it means basically if you train a model on GFT 300 millions, you can do like 5-shot learning on the ImageNet and get about like 70%.
What is 70%?
It's a accuracy. It's top
accuracy across some data set, right? How many samples in that data set?
So basically you're training, for example, on 3 billion data set, and then you're taking this model and you have a small task, for example, and you're giving just 5 samples per class from ImageNet, and then you're testing it on ImageNet ImageNet holdout set.
Okay, so you're testing it once. It's really just one point that you're plotting and comparing
Yeah.
because you're looking at the accuracy or okay.
Yeah, so bigger models kind of solving future learning is better. And that
I don't
just
know,
shows-
is it better or no different because we don't have variance there, error bars or anything, especially between the green ones. They may be the same exactly, but the green and the black may be the same exactly as well, highly likely. I mean, I don't know. It's just like those figures are funny. They don't tell me much.
because in bigger scales like this, like 1%, it can be like 100,000 images, and so the parabola just won't make sense. It just because of scale. But there are clearly like 2% difference at least, or 3% difference of mixer with big transfer with resonance. But I think like you have to take it as a money point that this kind of models can work still. In like the main problem is like, are they like, for us it's like important if they are efficient in low data scenario, which is like more interesting to us. We don't have like so many labels and we want to learn some good representations. So I think it just like gives us tools to explore like our ideas. And I like how like mixer can be connected to ICA because it kind of has the same structure to some degree. And just to continue on results, mixer was outperforming on ImageNet by gated MLPs and RS MLPs. And then you can see there is like parameters. So Git MLP has 73 million parameters and it got 81.6. And there is a conf mixer which has only 51 million parameters. In 150 aperage, it's got 82% almost. And it's interesting that this conf mixer outperforms Resonate 152. It outperforms, there is data efficient transformer. Vision transformer is basically a vision transformer which uses additional distillation from pre-trained network like convolutional network. And I think it's kind of interesting to see that it's not about architecture, it's about more patches, like how you construct your model. Like basically, like I said, it can be like viewed as a bag of words, where like all the words in your bag interacting with each other, instead of just creating a representation of one word in the bag. And I thought it's kind of related to segmentation project I did with MeshNet, and I think it's also related to ICA, like to some degree.
And it's related to graph networks.
Which one? Sorry.
Graph neural networks.
Crap.
Graph.
Sorry, I did.
Graph neural networks.
GNNs.
So sorry, I don't recognize the word. I don't.
The graphs.
Graph neural network. I see. Yeah, the graph. Yeah, there is. I think there is a paper connecting transformers to graph networks. Yeah, there's exist. Yeah. I think graphs are nice because it's kind of another way of viewing on neural networks. And I think there is like can be connection to this reservoir computing. Yeah. Yeah. So like the model scale of mixer kind of comparable to visual transformer, and the scale of the model better than CNNs. That's why mixer or transformer are interesting to the Google or other Facebook big companies. But there is like paper which was shown recently. It basically says that we have like some limitation on scale. For example, there's two definitions called upstream task and downstream task. Something upstream task is basically the task you're using to pre-train your model, or like it can be simple classification on ImageNet. And downstream task is basically when you transfer your model to some different task. And by running like 1,400 MLP mixer or ResNet or vision transformer models, they found that there is situating behavior that you can get, for example, 100% accuracy on your upstream task, or like 90, but your downstream task will be saturating, even you improve performance on your upstream task. And the main claim, I think, the paper saying that scaling doesn't lead to models that are helpful for every kind of solution, and they also have like some ideas that about your depth of neural network. So when we improve upstream performance, we kind of we can see that high layers of these models are more important for upstream performance, and low layers are more important for downstream performance. So I think it's kind of connected to the idea that higher layers memorize some specific features to the task, and lower layers are more important for transfer. I think there is a paper by Rakhu. She explored how ImageNet models transfer to medical imaging application, and she was showing that if you take lower layers, they transfer better, or you can use even like Gabor-like initialization of the features, and also get quite comparable performance. And I think it's interesting because you can understand that scaling doesn't solve everything, but there is still like a positive note that if you want to improve your performance on your task by scaling that set of models, it will help you, but it doesn't like solve everything. And also I think the other interesting paper to read, it's called Under Specification, and I attached here. And it's interesting in the sense that it explains you that even you're training a lot of models and they can get like similar performance, but the learned features in this model will have different kind of behavior when you transfer them to different tasks, or like applying to different scenarios. And for example, in healthcare, for example, we can use like supervised model on two-class classification, like health and Alzheimer, over different iteration. Specifically in small data regime, you might get different kind of features that explain this disease, but some of them can be like wrong, because we can meet this like
Alex.
Yeah.
I mean, I don't want to interrupt, but they told me to interrupt because you can't see my hand raised. So I'm interrupting because of the shirt. It's such a, I mean, like, it's just a kind of like, I'm sure it's just like a joke kind of thing, but but it's on the slide, so I can comment it. There just seems to be so many things not solved in deep learning that scale is all you need. And AGI is coming seems like such a optimistic view in my world. Like spatial reasoning doesn't seem to be solved that well, and like causality is not solved. And I mean, I certainly don't know all the literature on all these things, but like saying scale is all you need, like that's such a extreme statement in my mind. Like, is it justified? Am I that out of touch? Or is it?
Yeah, so I think you have to take it different way. I think reasoning, I agree that reasoning is important, causal relationship are important, but I think the most important stuff is to learn representation. And we kind of on the way to solve representation learning problems. And then we can kind of go towards reasoning, how to interact. But I don't think like we can solve just by doing this, but maybe like reasoning have to interact with representation learning, efficient representation learning together to solve this. And we have to have reasoning because this kind of models, they just learn representation and scale for them is important. And that sets are important because there are like more questions like, I think of data efficiency. The main question, I think data efficiency should help us because we don't have like every time compute like this. So we can't just like scale that sets. We can't just like scale compute. And of course we see that like this doesn't solve all the like real like properties of artificial intelligence. Like you can see there are like GPT-3, there is a clip, they do nice thing, but like they're failing on stupid stuff. And there is like a lot of cases where they fail. And I agree that like we need like some reasoning for this kind of models. But we also need to learn like good representation. And I think we are very close to like learn good representations to some degree, but it like will never stop, I think.
So so you're saying that learning good representation will solve reasoning problems?
No, it doesn't solve reasoning problem. It will help solving reasoning problem. Once we learn representation of entities, we can manipulate with, for example. I think this is how we solve it. We can't reason without knowing entities. Like we need to create this. For example, we need to create nodes to connect them with the edges.
And this is a deep philosophical problem, actually, because as we know easily in the brain, what are the entities? Neurons, atoms, components. Yeah, what are they?
No, but yeah, exactly.
Yeah, I mean, I accept that the brain acts in a distributed way, probably, and that's not.
Which is just a word, by the way.
Yeah.
Like.
Okay, let's just move on a bit. I have like 2 minutes. I'll just show like a couple of slides I have. We can think about it more, of course. And I will skip this because we understand how like size influences the performance already. And I'll suggest to read this paper. It's very new, but it basically covers a lot of these models. And
can you post it in the reading group, please, after the meeting?
Yeah, I can do. And they also defined the scaling law. So basically using this law they have, you can estimate your performance, like predict your performance. So basically, if you run like multiple experiments, your experiment will be within like some convex hull. So basically this is a contribution, but this paper is new. I read like only how, but it's interesting. And I suggest also read under specification. They all connected and explains to you more about like how you should do in machine learning and what you have to be cautious about. Yeah.
Alex will be presenting this paper.
But in December. So invariance linked to permutation. It just shows that to patch and pixel shuffling, Mixer is more robust than ResNets. And it's more robust to global shuffling, but it still drops performance. So you can see that like CNN are bet on this kind of scenarios, but it's just because the way how they constructed, I think. But the Mixer or visual transformer gives us like nice properties. And this is visualization. They showing this is showing that Mixer allows like global information exchange. That's why you're seeing this opposite direction, big kind of filters. And it's also like Gabor-like, and you have this opposite bases. So you have red and blue, and I think they're taking it from token mixing, as I remember. Yeah, and I think yeah. So this is conf mixer. They also have visualization of the features, and they also say it's Gabor-like. Yeah, so I'm not sure how it helps right now, but it just connects us, yes. And technically, what people looking at, they looking at infinite data regimes, scaling laws, and we kind of behind in the sense because we don't have like that much data in healthcare or like even like our studies. So we have to find a way like to like advance science through these deep learning methods. And the interesting thing, I just by construction, like it reminds me this Dr. Calhoun's images with ICV, and you can see how like Mixer kind of having the same structure. And I think this can like we can try Mixer models and try to think how we can kind of construct better deep learning models, but inspired by ICA and recent advances like Mixer. Yeah, I think that's all from my side. Yeah.
Thank you, Alex. I will have to finish now because of a meeting
Yeah,
that's
sure.
already started.